Good. Good. Glad that conversation wasn't in the video. All right, welcome, period 8. You are watching this over break because your class is too slow for some reason. Period 7, the real people who are in the room right now, we're going to talk about Gottlob Frege. One of the most important mathematicians of all time, one of the most important philosophers of all time, most influential philosophers, one of the most important, probably like 3 logicians ever, and has just like profoundly affected thought of the 20th century. I took an entire class on Frege in college. In fact, it was like a Frege-Russell-Wittgenstein class. And I will now try in half an hour to say some things about him, and then the rest we'll say after break. All right, what's his deal? Well, he is German. He was born in Germany mid-century. His father wrote some German language textbook, which included a section about logic. He studied at a gymnasium. That's sort of like the old Roman Empire term for just like a school. Went to the University of Jena. And eventually attended Göttingen, which that city has come up a couple times in this class. It's basically the University of Göttingen becomes kind of like the #1 university in Germany in this era, and Germany is basically the #1 country in the world to do mathematics. His PhD thesis or doctorate was on a geometrical representation of imaginary forms in a plane. So he was sort of doing this very kind of abstract projective geometry, basically, trying to kind of model it using other things. So he's very much like a mathematician by training. And he was right, at this time, this is the 1870s, this is like the era of Weierstrass, right? So he is right there in the middle of it all. So he's getting it kind of as it's happening. And so you should sort of think of him initially as just another guy who is attempting to rigorize mathematics. But he takes rigor to a whole nother level beyond which you could possibly have imagined. And it's not very popular. And basically he has these incredibly influential writings which are more or less ignored. And in his sort of major career, which is from sort of the 1870s to about 1905 or so, he sort of forever changes logic, philosophy of language especially, and to some extent mathematics. Kind of one of the greatest philosophers ever, that's my opinion. Were it not for Bertrand Russell, who kind of sort of, I don't want to say discovers him, but Bertrand Russell brings him sort of to prominence later, and they have kind of this interesting sort of mutual relationship, which also comes up in logiconics. Okay, what does he do? Well, all right, imagine you're back and it's 1870, and you're attending a Weierstrass lecture, and Weierstrass says, we're going to prove the intermediate value theorem. And what he does is basically exactly what we did 2 weeks ago when we proved the intermediate value theorem. We had the definitions of continuity as an epsilon delta proof. We had the least upper bound axiom, and we went through. Does everyone recall? Nod your head gently if you're like, yeah, Mr. Rose, I remember we did this, right? And we proved the intermediate value theorem line by freaking line with just definitions. Absolutely no intuition was required. Well, says Frege, if that were so, I would be satisfied. But I'm not satisfied because, after all, in order to follow this proof and to be sure that it is correct, I need to use tons of intuition. What is the tons and tons of intuition that is required in order to process and determine valid the proof of the intermediate value theorem, such as we did in class?
Deductive logic steps?
Like deductive logic steps, right? And so Frege says, look, we haven't truly rigorized mathematics until we have rigorized the underlying logic of mathematics. And so he decides, I'll just do that. Give me a few years. In the 19th century, it is often has been said, and this is barely an exaggeration, that the field of logic had not really changed since the time of Aristotle. Aristotle is the first person that we have record of who sat down to just like write all of the actual principles of logic, and he does so. And he does like a halfway decent job for propositional logic, and for predicate logic it's like kind of terrible. So okay, other people made this slide, so it's sort of weird that my name's on it, but you know, in Aristotle's logical works, which were studied by you know, not just generations, thousands of years literally of people, especially during the sort of Middle Ages tradition, who just were obsessed with Aristotle, would just read these books over and over again, and there was this whole thing that's referred to as term logic. So a term is like a part of speech. But they didn't distinguish between what we would now call sort of singulars and universals. So like, you know, Mr. Rose or whatever is a term, but so is like humans a term. Anything that you sort of would think of as like a noun is like a term. It's a very kind of like sort of part of speech based kind of a way of analyzing things. And then, okay, a proposition can be true or false. And what they attempted to do was to, what Aristotle attempted to do was to explain what it means for these sort of syllogisms like all humans are animals, all animals eat, therefore all humans eat. This seems like a valid logical argument, and so Aristotle tried to explain what makes it valid. And what happened was like this kind of confusing nightmare of very special cases. So he divided, Aristotle did, all possible quantified sentences into the forms all S are P, no S is P, some S are P, and some S are not P. And if you were a logician in ancient Greece, or for that matter a monk in the Middle Ages in Europe, or for that matter anyone really in any university in Europe through until 1850 maybe or beyond, you would spend, you know, endless months or years like studying logic. And what that meant was studying the so-called square of opposition. And I don't even remember all this crap, and I don't really quite care, but it's like a nightmare of A type, I type, E type, O type. Things on the opposite corners of the square of opposition are contradictory, then other things are sub-contrary. I don't remember what that means, subaltern. This was basically logic. And in the mid-19th century, finally, there was some advancement in this, from this sort of terrible system that existed, with Boole at first, who tries to turn logic into a kind of an algebra, but that was really just propositional logic. And finally, Frege. So Frege says, this is terrible. We are in an era when in order to do proofs, we need like quantifiers, man. And so what he does is expand our vocabulary and basically introduces quantifiers in their modern form. The problem with what was going on, the problem with Aristotle's logic is that it was essentially the thing I made fun of back in like September when I tried, before I introduced natural deduction. It was a set finite number of logically valid arguments, which were essentially just stipulated as being logically valid, and then you just had to kind of learn them. Like, so if all you ever want to do is say things like, Socrates is a man, all men are mortal, therefore Socrates is mortal, then great, Aristotle solves that problem for you. And if all you want to say is that no reptiles have fur, and all snakes are reptiles, so no snakes have fur, then again, the Aristotle square of opposition is for you. But like, we need more than that, man. In fact, we need just like the full range of quantified logic in order to do mathematics. And so this first sentence, for all epsilon greater than 0, there exists a delta greater than 0, such that for all x, if x, absolute value of x minus a is between 0 and delta, then absolute value of fx minus f of a is less than epsilon, is our modern definition of what it means for f to be continuous at x equals a. And this language which we maybe now find so natural because like we've been doing it all semester, simply just did not exist at the time. At this time, people were still just writing it out like in words. Or well, okay. The characters existed. That's true. I think Weierstrass was using characters like this and even wrote out definitions like this. So I retract that. But what Weierstrass did not do is attempt to give any rules whatsoever for how one reasons correctly using quantifier logic. Weierstrass just took it as understood that the various steps in his proof were logically valid. And so we now had sort of a level of rigor in which there were certain symbols and principles being used, but those principles were completely unexamined. It is sort of famously true that without this is an example that's often cited, with only like Aristotle's logic, you can't even say things like that there are an infinite number of primes. But with the sort of modern quantifier logic, we have this sentence. Let's parse it together. You had almost something exactly like this on your quiz. That there is no largest prime. But here now I have instead of taking prime as like instead of taking prime as a primitive, I am defining what it means to be prime in terms of piano arithmetic. And so what we have here is for all numbers, there exists an m which is bigger. In other words, for any number, there's always a bigger one which is prime. And what does it mean to say that m is prime? Well, if m is prime, all that means is for any possible number, that basically that if you can find two numbers which multiply to be m, then they're either 1 or m. Okay, there was no notation to express these ideas unambiguously. There was kind of a general use of terms like this, but not really. And what there was certainly not was any organized analysis of the validity of any sentences involving quantifiers, pre-Frege. And so everything was just unformalized and intuitive. All right, so Frege says, dude, how do you know that these statements actually follow from the axioms? If no intuition is supposed to be allowed in mathematics, for mathematics to attain true rigor, we must be able to explain why one step follows from another. We haven't really gotten rid of reasoning from the diagram until we get rid of having to use intuition to get us logically from one line to the next. And so he sort of dwells for a really long time trying to figure out how to do this. And he gets very philosophical about it and decides, okay, sentences like all men are mortal and Socrates is mortal, these appear superficially similar. But really this is just like an artifact of English grammar. They are both in the form subject-predicate. But in fact they're two totally different things. When we say Socrates is mortal, what we are doing is we are asserting that there is some concept is mortal, and that concept is applicable to Socrates. Okay, it seems reasonable. But when we say all men are mortal, we are saying something totally different. What we are really saying is that there's a concept men, or is a man, and a concept immortal, and this all functions as a kind of relationship between these concepts. Okay, and he sort of kind of explodes sort of forever this shallow analysis of kind of like how sentences are structured. All right, and then he says, okay, I'm going to do logic. And he does it. This is the preface of his first work in the 1870s. He says, okay, the most reliable way of carrying out a proof, obviously, is to follow pure logic. A way that, disregarding the particular characteristics of objects, depends solely on those laws upon which all knowledge rests. I like that. Accordingly, we divide all truths that require justification into two kinds. Those for which the proof can be carried out purely by means of logic, and those for which it must be supported by facts of experience. But that a proposition is of the first kind is surely compatible with the fact that it could nevertheless not have come into consciousness in a human mind without any activity of the senses. Okay, so what's he saying here? What he's saying here is that even though, this is kind of a Kant type comment to make, that really it is not how one comes into consciousness with a fact, but whether it's really the support of a fact which is relevant, right? even if you may have learned about a fact, if you could have learned about the fact without experience, then we say that it is carried out purely by means of logic. In other words, he wants to say it is not the psychological genesis. It is not. This is kind of like a statement of his entire program. It is not how we first learn of a concept which is relevant, but the method of proof that is at the basis of the classification. If you can prove something by logical means alone, then it is a priori, regardless of whether you perhaps learned of it first via some other means. Yes?
What are you proving it from?
Yeah, good question. Okay, now, he says, he's talking this out. Now, when I came to, what are you proving it from? I think I can answer that. From those laws, solely on those laws upon which all knowledge rests. Okay. So Frege says that there is some sort of logic which just you have to accept. If you don't accept it, you have nothing at all. Okay. All right. When I came to consider the question of which of these two kinds the judgments of arithmetic belong, okay, here we go. He's basically sitting down in the 1870s and asking the really, really hard questions like, why do we know arithmetic truths? Where do these arithmetic truths come from? Are these arithmetic truths somehow based on logic alone, or do they come from somewhere else? And if they come from somewhere else, like where? How do we know that our arithmetic is true? And he says, I first had to ascertain how far one could proceed in arithmetic by means of inferences alone, with the sole support of those laws of thought that transcend all particulars. In other words, I'm going to lock myself alone in my basement. I'm going to give myself only those laws upon which all knowledge rests. In other words, logic only, nothing else. And I'm going to see how far I can get in justifying the truths of arithmetic. Are you with me? All right. My initial step, says Frege, was to attempt to reduce the concept of ordering in a sequence to that of logical consequence. So somehow he wants to sort of capture even the notion of what it means for things to come after one another in a sequence, using somehow logic, and as to proceed from there to the concept of number. Okay, but here he says he finds this really hard, because if you're doing extremely careful reasoning, at which you are trying to be very, very careful that no extraneous facts kind of like pollute your thought, then you need to be really, really careful. And he keeps getting frustrated that his notation and that his reasonings can't be made careful enough because there simply is no system for judging whether one thing follows from another. To prevent anything intuitive from penetrating here unnoticed, I had to bend every effort to keep the chain of inferences free of gaps. In attempting to comply with this requirement in the strictest possible way, I found the inadequacy of language to be an obstacle. Okay, this guy is saying, okay, Weierstrass, you banished intuition from mathematics, but you're still just doing math in German. And therefore it is possible that when one is just speaking simple human language, then some intuition can penetrate unnoticed. We can have no intuition in mathematics. We must banish all intuition, for otherwise how do we know that our proofs are actually correct? And he says language is simply inadequate. Language is an obstacle to understanding because it is not precise enough. No matter how unwieldy the expressions I was ready to accept, I was less and less able, as the relations became more and more complex, to attain the precision that my purpose required. This deficiency led me to the idea of the present ideography. Its first purpose, therefore, is to provide us with the most reliable test of the validity of a chain of inferences, and to point out every presupposition that tries to sneak in unnoticed so that its origin can be investigated. In other words, we must construct a formal language which is completely precise, in which all of our thoughts and all of our mathematics can be written down in an unambiguous manner. In other words, we need predicate logic. Are you guys following this? Are you inspired by this passage as I am? Okay, maybe not. Anyway, we move on. Yes?
Why did we not talk about this when you were introducing?
Because we weren't ready. We weren't there. We had to transcend the age of rigor before we could see why this was relevant. Okay, so he produced his first famous work is the Begriffsschrift. Okay, this is a German word that we will all learn. It's quite simple. Begriff is a concept, and Schrift is like a writing, like script. Same kind of thing. So everyone say Begriffsschrift. 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 It is a concept notation. It is literally a notation for explaining your concepts. And what we have is, for the first time, a basically first order logic. And here's his notation. He says, okay, he even is so careful that he distinguishes between the mentioning of a proposition and the judgment of a proposition. The judgment is the assertion that a proposition is true, which is distinct from the proposition itself. This is a distinction that no one else had previously talked about in the history of philosophy. If you want to take the negation of a proposition, you just stick a little thingy in front of it. Cool? Say cool. A conditional can be written like this. This means Q arrow P. So you read it like chunk, like that. Cool? Okay, and as we know, not and arrow are an adequate set of connectives, so he doesn't bother with and or. Okay, this sort of says logical equivalence, although he treats it a little bit differently than we do. Universal quantification is represented with this little boop, so it's for all x. V of x, am I in people's way, kind of? And existential quantification, which we know is also not completely necessary. Existential is just not for all not. Cool? Okay, he invents this notation, and here are some examples, right? So the first one is sort of saying A is true, or I judge A to be true, or I prove A, or I have A, or something like that. Okay, this is not A, this is B arrow A. If I want to say A and B, then that can be represented as not B arrow not A, so that's jump jump. And then this is not B arrow A, is A or B, and okay, cool. All right, and here is his various ways in his system of saying the sort of basic kind of Aristotelian logical facts. So I should say also that I have this book. It is called From Frege to Gödel. It is this is just a collection of primary source documents from the sort of golden age of logic or something, which begins with this paper, the Begriffsschrift, and ends in Gödel's incompleteness theorem. And so the first paper in here is the Begriffsschrift, and you can just pass it around and check it out. And yeah, whew. What does he do? So anyway, do we need to go through all these, or just kind of fine?
No.
Good. Woo. All right. His logical system is not a natural deduction style system. Natural deduction comes later. His system is a so-called Hilbert style system, in which, you'll see. There are three sort of axioms of propositional logic, but then only three rules of inference. Okay, so here are his axioms. This is completely unlike anything we have done in this class before, and I don't really feel like going into the details of it because it's hard and annoying, but it's a thing. And take number one. That is an axiom. In modern notation, it would be represented as A arrow, B arrow, A. But of course, he does it with his own system like that. That is a tautology. It's true. And two is this other strange axiom, also a tautology, I promise. And three as well. Okay, with these three axioms, so to speak, one may prove all possible propositions of propositional logic with only one rule, the one rule being modus ponens. Okay, so this is a heavy on the axioms, light on the rules type system. He wants just one rule, modus ponens only. And as he has only one connective besides negation, I guess I need a couple more. I have a couple more. I think I need one more axiom. Yeah, I need the axiom that gets negation involved. I need a couple more actually. Yeah. So I have an axiom that says basically law of contraposition. I have a sort of negation intro and elim axiom, and then he's got basically one rule for universal elimination, and he has kind of it's a function rule, some rules about how kind of biconditionals work, and he's got a substitution rule in there too, I think. Anyway, from this you can prove everything. And he just goes through and just proves that his system works. And then he just goes, so you have 3 rules of inference, sorry. You have modus ponens, generalization, and substitution. Okay, here's an example of a simple proposition in Frege's work. Can you see how maybe this was not immediately adopted by the contemporary mathematical community of the 1880s? This is like some terrible, basically their reaction was kind of like, Kevin, can I make fun of you for a second? It's like Kevin's reaction to when I'm giving him these Fitch-style proofs. He says, why am I doing these? What do I need these for? I already know all the math. This does not help me do math. Only for someone who is extremely interested in the precise details of exactly this particular argument in my very, very low level math proof actually follow, or am I sort of letting it get corrupted by what I want to be true? Would such a system be sort of of value to you? And basically this just like falls like a brick, man. No one adopts it. It has 0 readership and it just goes away forever. In modern notation, which is largely due to Peano and is then popularized by Russell, we would say some stuff like this, which is still pretty hard. Okay, he goes on in this like 60, 70 page thing, which is making its way around the room. It's also to here, you can look at it another time, to sort of eventually try to build out of logic alone the very notion of what it means to be a sequence. Okay, step 1 in his 5-step plan to assure all mathematical truths. Step 1, axiomatize predicate logic. Check, done. Step 2, figure out where logic ends and math begins. We must know whether arithmetic truths come from the laws of thought alone or come from somewhere else, and if they come from somewhere else, where? Well, before we can truly answer this question, we must know what numbers are. If we can somehow know all math can be reduced to numbers, and if we figure out what numbers are, we're good. Well, before we can figure out what numbers are, we must figure out what words mean. And only then, and then we can establish all mathematical truths. Yo.
So this is like the brought reverse order?
He realizes at each stage that he can't achieve his program until he comes up with a formal logic to make sure that his math proofs that he can follow his own mathematical reasoning. And then he tries to take it as far as he can go. But before he can get any further, he has to figure out what numbers are. And before he can figure out what numbers are, he has to figure out what words mean. And he, one by one, over the 1880s and 90s, completes all of these tasks, at least to his satisfaction. Okay. Something like that. He thinks he does. Okay. Oh man, I really wish I had another hour. Oh well. His next major. What should we do? Should we just give up and stop now?
Yeah.
Okay, good. So in his so-called Grundlagen, everyone say Grundlagen. Grundlagen. It's German. No, we have 3 more minutes. We're going to the end. Grundlagen is German for, I guess, foundation, kind of like ground laying sort of type thing. The foundations of arithmetic. And this is titled A Logical Mathematical Examination of the Concept of Number. This is it right here. I've read this entire book. I've reread the first 40 pages of it like a couple weeks ago. It is so good. This is like such incredibly good philosophy. It is just philosophy of the highest, just perfectly clear language. Everything he says, you're like, oh yes, you're so right, you're so right, you're so right, you're so right. And what he does is he single-handedly really, well, a couple people, but he's really primarily responsible, takes philosophy into like the modern era of philosophy. He basically takes a mathematician's level of precision towards his philosophical thinking, and he has mathematical levels of like rigor that he applies to his philosophical thinking, and he more or less kind of single-handedly, although other people are also responsible, begins this sort of era that we are still in now, and at least in the English-speaking world, called analytic philosophy. Analytic philosophy is philosophy in which you really, really care about being extremely precise about the exact things you are saying and the words you are using. You define your terms really, really clearly, and you try to reason with sort of respect for like the logical inferences that you're making. And he sets out in this entire book to figure out what numbers are. and he does it to his own satisfaction. And again, almost no one reads it. Bertrand Russell reads it, finds it to be exactly the kind of thing he was looking for, and sort of popularizes Frege in a kind of a way. He is the first person to distinguish between sort of objects and predicates. Predicates as in like sort of properties that some object can have. And he applies, again coming from the mathematical sort of background, he applies a kind of like function type analysis to predicates. The way that we now talk about sort of predicates as sort of applying like a function does to an object is he's sort of responsible for this. All right, I guess I will stop and goodbye, period 8.